Welcome back to this explainer. Let's dive right into part 2 of our breakdown on clearance rules and carrier classes, moving directly from hazard ratings straight into the physical steel of the ship.
As a quick recap from part 1, remember that ship type ranks cargo hazard severity from 1G, think highly toxic cargoes like chlorine, all the way down to 3G, which covers your typical LPGs. Now, let's take that theoretical hazard ranking and turn it into real practical ship design.
Section 1. Hazard rankings to hull clearance.
So, higher hazard ship types actually require a much greater minimum clearance between the outer hull shell and the cargo tank itself. And this required distance applies to both the side and the bottom shells. The engineering logic here is pretty straightforward, right? If a collision or a grounding is severe enough to breach that outer hull, you absolutely need a real chance of leaving the internal tank completely intact.
Because the acceptable consequence of a breach is just drastically lower for a highly toxic 1G cargo, its tanks sit noticeably further inboard than a 3G ship's tanks would, even for a comparable size vessel. Building a 3G ship simply gives you way more design flexibility to push those tanks closer to the outer shell.
Section 2. The 3 carrier classes.
Beyond just the ship type, gas carriers split into 3 distinct operating classes. First, we have fully pressurized carriers. These use really thick-walled Type C tanks at ambient temperatures and high pressures, up to roughly 17 or 18 bar gauge. Since they literally need zero refrigeration plant, they're remarkably simple and cheap to build. Then, on the complete opposite end of the spectrum, we've got fully refrigerated vessels. These use massive insulated Type A tanks, holding cargo near its atmospheric boiling point at just 0.25 bar gauge. But the catch? They require incredibly complex, full onboard refrigeration plants to work.
And then, well, we have the middle ground. Semi-pressurized carriers sit deliberately right in between. They use Type C tanks with partial refrigeration, which brings the pressure down to a moderate 5 to 7 bar gauge. That partial refrigeration is a real game changer because it lets you build smaller, lighter tanks compared to a fully pressurized design, but without taking on the massive capital expense of a fully refrigerated plant.
Now here is an absolutely crucial takeaway. Choosing the wrong pressure class for a given trade route, that's a massive commercial mistake, not just a technical one. If you misalign the engineering here, it directly drives up your new build costs, severely limits your cargo capacity, and completely bloats your operating expenses for the entire lifespan of the ship. Nobody wants that.
Section 3. Let's do a quick refrigeration knowledge check.
All right, quick check to make sure we've locked in these engineering extremes. Which of the 3 carrier classes we just discussed relies entirely on a full onboard refrigeration plant to keep the cargo near its boiling point at low pressure?
If you guessed fully refrigerated, you hit the nail on the head. Because the pressure is just so incredibly low, it literally only works if an active plant does all the heavy lifting. It has to continuously remove the heat that naturally leaks into the tank throughout the entire voyage.
Section 4. Engineering summary and next steps.
Let's step back for a second. Before this 2-part explainer, you understood containment architecture, but maybe had no sense of how the whole ship gets classified around it. Now, you've got the full picture. Ship type ranks the cargo hazard, which dictates the real, physical clearance distances from the hull. And finally, the vessel is built to one of 3 pressure classes, perfectly balancing tank cost, size, and plant complexity for its route.
And all of these physical engineering choices directly dictate a vessel's cargo worthiness. You see, seaworthiness isn't just about the hull and machinery being fit, it's about the legal fitness to carry a specific cargo safely. For gas carriers, the containment system must be perfectly fit for that specific gas. And owners are legally obligated to prove this before every single voyage.
Well, that officially wraps up our look at containment and ship design. You now understand the cargo and the physical ship. Next, we're going to transition directly from the physical steel into the business layer that's wrapped around all of it.
Now that the steel and physics are completely locked in, how exactly do legal frameworks and charter structures determine who gets paid and, maybe more importantly, who pays the price when something inevitably goes wrong? We'll cover all those legal and commercial structures in our next explainer. But for now, thinking about the engineering and commercial risks we just covered today, what physical design choices would you reconsider if you were building out your own fleet? Leave that thought with you, and I'll catch you next time.